This is the fourth of a 7-video series on factoring, monic trinomials. Let's break down some of this vocabulary. A trinomial is a polynomial with 3 terms, 1, 2, 3. And we're going to focus on trinomials that have a constant term, a linear term, meaning an x to the first term, and a quadratic term, meaning an x squared term. Monic is a fancy math word that means having a lead coefficient of 1. Now that 1 there is rarely visible, and we simply write x squared. And when you have a monic trinomial like this, there's a great procedure that you can follow, which we'll get to in a minute. But first, some more vocabulary. The coefficient of the linear term is cleverly called the linear coefficient, and this is called the constant coefficient. I'll just call it the constant. And these two numbers turn out to be the key to factoring a monic trinomial, as we'll see. Now, in general, there are 2 outcomes that can happen when factoring such a monic trinomial. One, it factors into 2 binomials. Or 2, it doesn't factor at all, in which case we call it prime. Now, if you were to consider all monic trinomials like this with single or double-digit coefficients, it turns out 90.4% of them are prime and don't factor at all, whereas only 9.6% of them actually factor. Now, this particular problem is factorable, as we'll see. And interestingly, in mathematics courses, we spend almost all of our factoring time on this 9.6%, on this rare type of trinomial. And so, even though about 90% of trinomials like this are prime, you won't see many of those because your professor or textbook will probably have made up problems in that special 9.6%. So you start to get a sense that almost everything factors when it really is more rare than it might appear. So let's get into the specifics of how to go about factoring. First, each binomial should start with an x. This essentially comes from the fact that when we multiply these 2 together, we're supposed to get the original problem. That is what factoring is, after all. And so by placing an x at the beginning of each binomial, I ensure that when I multiply them out, I'll get an x squared and thereby match the original problem. But at its core, factoring is ultimately guess and check. I'm going to make a bad guess, but we're going to learn a lot from this bad guess. I'm going to put 2 random numbers here, and I'm going to pose the question, is this the factorization of this monic trinomial? So if you're wondering where the purple numbers came from, random guess. But like I said, watch what we learn from this random guess. Now, if this is indeed the factorization of this monic trinomial, which by the way it's not, but if it were, if I were to multiply it out using the FOIL process, I would get the original problem, which of course I don't. Now, before we go any further, if you're not familiar with FOIL, or at least this kind of multiplication under another name, I highly recommend going back and watching a video called Polynomials Multiply, which I've produced. If you are comfortable with this kind of multiplication, let's move on. What we notice here is that the purple numbers add up to the red number. And the purple numbers also multiply to make the green number. And this, by the way, is a nice shortcut for multiplying monic binomials. But of course, we know that this guess, my purple number guess, is wrong because when multiplied out, it doesn't yield the original problem, which is the goal of factoring. So what we need are numbers here that when multiplied will be the constant and when added will be the linear coefficient. And that's our goal on this problem. So now the guessing will begin. Now there's two ways to approach this. One way would be to randomly guess numbers that added to negative 13 and hope to get lucky that those numbers that added to negative 13 would also multiply to make negative 48. And while there's nothing wrong with this, I've found more success doing the problem the other way around. In other words, I find it faster to look for numbers that multiply to make negative 48 and see, by guess and check, which pair happens to add to negative 13. So I'm going to start by making a list of all things that multiply to make negative 48. Now I'm not thinking about the number 13 right now. I'm just thinking what times what is negative 48. Here's an example. Here's another example. Here's another example. And I'm going to continue making a list of all possible ways that two numbers can multiply to make negative 48. If you need to pause the video to confirm that these all multiply to negative 48, now's a good time to do that. Now most of these are familiar to the typical student. It's very common to know that 12 times 4 is 48, for example. You'll notice there's a rare one in here that you don't see very often. The typical student doesn't have it stored in their brain that 3 times 16 is 48, but it does in fact work. Now, remember my goal, if you look at the top of the screen, my goal is to find two numbers that multiply to make negative 48, but also that same pair of numbers has to add to negative 13. So I'm going to add every single pair that I have here. Add, add, and I'm going to add them all up. And again, if you need to pause the video here to see the addition, now would be a good time. And now that we see that each of these pairs has been added correctly, one thing should catch our eye right here. That is the magic combination I was looking for. I was looking for a pair of numbers that would add to make negative 13 and also multiply to make negative 48, and that's exactly what I've found here. So what that tells me is that I've found my two numbers. So I've put them in my factorization. Of course, it doesn't matter where you put them. I could have put the negative 16 first. And I'm essentially done with this problem now. But here's something worth noting as an afterthought. If I have factored this monic trinomial, shouldn't that mean if I multiplied my answer back out, I would get the original problem? Well, if you were to do FOIL, first times first, outer times outer, inner times inner, and last times last, and combine like terms, you would in fact get what you expected. Now that we've seen an example of a monic trinomial that is factorable, let's look at an example of one that isn't. Here's a monic trinomial. Let's try to apply the same technique that we did to the last problem. Let's assume we can factor this into two binomials, which, by the way, it turns out we can't. But putting that aside and pretending we didn't know that, if we were to try to factor this, we would put an x as the first term in each binomial, as before. And again, we're going to look to guess numbers that will multiply to 4, but the same pair of numbers has to add to negative 3. So as I did before, I'm going to think of all the numbers and pairs that multiply to make positive 4. Positive 4 times positive 1, that's 4. Positive 2 times positive 2, also 4. This product is 4. But a negative 1 times a negative 4 is also a positive 4. And there are other negative possibilities as well. I have some duplicates here, but it doesn't make anything wrong here. I probably could have done less. Nonetheless, I'm looking for a pair of these numbers that would add to negative 3. Those add to 5. Those add to 4. And what we see is that of every possible pair of numbers that multiplies to make positive 4, none of them adds to negative 3. That means that the two numbers I'm looking for don't exist, and therefore this polynomial is prime. Let's now look at our last example, which will show us a combination of the monic trinomial method and a method learned in a previous video. If you haven't looked at the video called Factoring 2 of 7 GCF method, now would be a good time to go look at that before proceeding. If you're comfortable proceeding, here we go. This is a trinomial, but notice it's not a monic trinomial and it doesn't have a quadratic and constant term like we're used to seeing. That's because it turns out you can factor out a GCF here, or greatest common factor. Notice all the coefficients are divisible by 2, and my lowest power of x is x to the 1. Therefore, I can factor out a 2x to the 1. And if you factor that out, you'll get this. Now's a good time to pause the video and convince yourself that that works. Okay, so far, this looks like a greatest common factor problem. In fact, it looks like a couple of the problems we saw in that video. But something's different here. If you look at what's inside the parentheses of the greatest common factor portion of this problem, you'll notice that that is a monic trinomial and that that may be factorable itself, in fact is. And one thing to keep in mind about factoring, in general, not just this problem, is that when you factor one polynomial into 2, one of those resulting factors may itself be factorable. And that's what's going to happen here. You see, this x squared minus x minus 12 is factorable into x plus 3 times x minus 4. And just to convince you of that, notice this times this is negative 12, and this plus this is negative 1. But there's the invisible coefficient of 1 here, and therefore that fits the rule of the multiplication and addition for monic trinomials. So now that I've factored the monic trinomial, which was one of my 2 original factors, I now have a total of 3 factors in this problem, and there is your final factorization of this trinomial. And that completes the 4th of 7 lessons.